All righty then. Enough of these exponentials. Let's go logarithms. Which is something we didn't do either in Calculus 1. Well, just a real quick reminder of a logarithm. What do we mean? If I have log base A of x, it's just kind of a convoluted way of representing a number, isn't it? What do we mean by that? Well, if you got the logarithm base A of x equals some number, what does that mean? Well, that means A to the y power, right, equals x. I'm looking, when I do a logarithm of some number, I'm looking for the power of this base, right? I'm looking for, y is going to be the power that gives me the x, right? Like if I'm doing the log base 2 of 8, I'm looking for 2 to what power gives me 8, right? So that's 3. That's what I mean by logarithm. We won't necessarily have to be doing logarithms, but that's in a nutshell what it means, right? It's a power. What power gives me, power of the base gives me that. Well, there's a lot we could talk about, but just for time's sake here, let's talk about, first of all, the natural logarithm, because that one will be the one most typically we encounter. We'll encounter a few others, but the natural logarithm by far will be the most often one we read. The natural logarithm, well, that gets back to base c, doesn't it? If I have the natural logarithm, which is represented by ln, that just means the log base e of x. The a is the base, so ln, that's base e. That's all you basically need to know. So it's logarithm base e. Okay? The other thing that I've got noted here we might want to remember is that if I have a logarithm of some other base, like base 2 or base 5, base 60, whatever it is, I can change that into the natural logarithm. That's always a good thing. It's by the change of base theorem. By the change of base theorem, I can say the logarithm base a of x is the natural logarithm of x divided by the natural logarithm of the a. Hence, changing from logarithm base a to logarithm base e, the natural logarithm. So, if I have a logarithm base 5, let's say, of x, well, I don't have to be stuck with that. I can just say, well, that's the natural log of x divided by the natural log of 5. Okay? That's the one we shall use. Okay? All right. Well, since we're in calculus, we need to talk about its derivative and integral at some point or another, I guess. But for now, the derivative of logarithms. We're going to kind of go at this a roundabout sort of way to figure out what it is, the derivative. Yeah, let's say we've got just y equals the ln of x. Y equals the ln of x. Well, if I wanted to, I could change that to the exponential form. Remember, I didn't really label it, but if I've got logarithm base a of x equals y, in log form, then the exponential form is the base a to the y power equals x. Well, let's do that for this one. Change that over to the exponential form of that. What's my base? E. E to this y is equal to x. E to the y is equal to x. With me? That's just changing from logarithm form to exponential form. Well, if I then do the derivative of that, because I know a little something about exponentials of that, derivatives of that, right? Because that's just an exponential now. Okay? Now the thing of it is, all right, let's do the derivative. Let's d dx both sides. What's the d dx of e to the y? Well, e to a power is just e to a power, right? The derivative. The only thing is I'm doing the derivative with respect to x, so I need a dy dx, don't I? Now what's the derivative of x with respect to x? 1. Okay. Well, what am I trying to find? I'm trying to find the derivative. So here, let's solve for dy dx. Move that on over there. Wouldn't I divide by e to the y? But what does e to the y equal? Here. E to the y equals x. So can I just say that's 1 over x? Here's the story. If I have the natural log of x, my derivative is 1 over x. The derivative of the natural log of x is just 1 over x. Now what's significant about that? There's no logarithm in the derivative of the natural logarithm. If I have a function, natural log of x, the derivative is 1 over x. Gets rid of the logarithm altogether. Now, of course, if it's the natural log of x squared, is that what I'm going to do with that? I don't have anything. All right. If I have y equals the natural log of x squared, well, the derivative of the natural log is 1 over whatever this was. It's a chain rule, isn't it, again? I'm going to have to do 1 over not x, but x squared. And then I'll have to multiply by the derivative of the inside, 2x. You with me on that? The derivative of this natural log thing is 1 over this, which is x squared. Then I have to do the derivative of the inside, which is 2x, and then simplify the c. So it winds up being 2 over x. But the point is, yeah. Your natural log derivative is just 1 over, natural log of x is 1 over x. Okay? Okay. So what do you got there here? Y equals, y equals the natural log of x squared plus 5x minus 3. Well, the derivative there, the derivative of natural log is 1 over, natural log of x is 1 over x. So anytime you have the natural log, you're going to do 1 over something. But in this case, instead of x, I've got this. Well, in this case, that's what 1 is over. Because that's what happens on the natural log. When you do a natural log derivative, it's 1 over whatever is in the natural log. However, you do have to multiply that by what? The derivative of the inside. It's a chain rule thing. 2x plus 5. Derivative of the inside. So I don't think anything simplifies there, no factoring or anything we can do. Let me get one more thing in here for today. Okay, so here's what we got. Let's think about this for a second. We're going to go to a little bit of integrating here because this actually fills in a gap we've had previously. If you think about, let's do instead of ln, let's do the ln of absolute value. Ln equals the absolute value of x. There's a reason I do that. If you think about it here then, if we go back to our piecewise defined function, because we got that absolute value, remember doing that? We'll recall lots of different things along the way here, but one thing we did with absolute value, remember with absolute value we said, well, that can either be x or minus x. Same thing we can do with that here. It's either going to be the ln of x or the ln of minus x. With me? It's x if x is greater than 0. It's minus x if x is less than 0. Or less than or equal to, whichever you want to put equal to there. It won't matter. Because here's the thing. Either way we go, look at this. Look at the derivative. Well, the derivative in this case, what's the derivative of ln of x? 1 over x. What's the derivative of ln of 1? Ln of minus x. Well, it'd be 1 over minus x, but I have to multiply by something else, don't I? Because I've got minus x instead of just x, it's minus x, so I have to do the derivative of minus x right here. What's the derivative of minus x? Negative 1. Well, what's negative 1 over x times negative 1? 1 over x. Yes. So either way you go, you got 1 over x. Question?
The logarithms are supposed to be bigger than 0, so in the second one, it's just like the definition by logarithms, it's
Yeah. Well, x is less than 0. X is less than 0, so I get a minus of a minus, so it'll be a positive. You see what I'm saying? Okay. So that's where it comes in a positive. You are doing the logarithm of positive. Okay. But here's the thing. Either way you go. So this is why we do that. This is why we would do that, because this gets us negatives and positive, because you're right. If we're just doing straight natural log of x, x has to be a positive. But if we do the absolute value, you can get the negatives. That's why we do that. So that's a good question. All right. But either way you go, what's the derivative of this? It doesn't matter. it's 1 over x still. So if it's the absolute value of ln of absolute value of x, the derivative is still 1 over x, you see. Doesn't matter. Still 1 over x. But here is the real story behind this. I mean, we won't encounter necessarily a lot of times do the derivative of the natural log of absolute value of x. Where we will encounter it is backwards, the antiderivative. Because think about this. If I have the integral of 1 over x dx, by what I just did here, wouldn't this be this? With me? If the derivative of this is 1 over x, wouldn't the antiderivative of this be ln of absolute value of x? Why would we want to put the absolute values in there? Because it gets us more values of x. If I just put the ln of x, that limits it because, like she was saying, you can't have the natural log of a negative number. You just can't do logs of negative numbers on real numbers. So the absolute value is an important part of that because x can be positive, negative, anything, except, of course, 0. You can't have x as 0. But that wouldn't be part of this domain anyway. Okay? So it works basically the same except for the absolute values. This, like I said, this fills in a gap because if I do, this is x to the negative 1 power. And remember when we were doing the power rule for antiderivatives, that was the one we couldn't do. We can't use the power rule on that, can we? Because if I use the power rule on that, I get x to the negative 1 plus 1 is x to the 0, so I'm dividing by 0, right? So that's why I can't use the power rule on x to the negative 1, or 1 over x. I can't use the power rule. It turns out it's a natural logarithm, the natural log of absolute value of x.